My name is Joan Sau, and I'm Sau Eduardo Seid. I'm also a PhD student here in UPC. And basically, until now, we have talked about AC-DC converters for HVDC applications, but we will see that we also need DC-DC converters in HVDC. So I'm going to talk about this issue here. Okay, imagine we have this conventional grid. It's a typical AC grid. We have different generation nodes. For example, we can have a nuclear power plant, hydropower station, and then also the consumption here of our house. In this grid, we have different AC voltages. We can have voltages of 400 kV, then lower voltages for distribution, and finally the 400 volts that we have in our houses. What happens when we introduce all this future DC grid that we are talking about in this scheme? Okay, if we have a DC grid, in this DC grid we will have different types of generation as well. For example, we can have an offshore wind farm here, which will be connected with HVDC to the main grid. And of course, we will have these AC-DC converters that we have been talking about. But as long as we have different DC voltage levels, in order to interconnect them, we will need DC-DC converters, because in DC, you know that we cannot use a transformer because it's useless. So in this situation, we will have different DC voltages, for example, for photovoltaic, power cells, battery energy storage, and even for charging the electrical vehicles. So we see that a DC-DC converter is also required in this scenario. If we talk about a more specific case, imagine that we have two links here, two HVDC links. This is a LCC link that Carlos explained us about that. It is connecting two AC grids in order to exchange power between them, and then we have here a MsC HVDC link, and this one is used in order to interconnect this wind farm which is in the middle of the sea, in order to extract the power and give it to the shore. What happens if we want to interconnect these two HVDC links? We cannot do that straightforward because these are different topologies. Here we have a MsC, which is a voltage source converter, and here we have an LCC, which is a current source converter. Here the current goes always in the same direction, and the voltage can be bidirectional, and here is the opposite. So in order to interconnect these two schemes, we need a DC-DC converter here in the middle. Even if we are talking about two different MsC HVDC links, the voltage levels of these two links can be different. So one can be 200 volts, for example, and the other can be 200 kV, and the other 400 kV. So we need also a DC converter in order to make the connection here. About DC-DC converters, we have mainly two topologies for HVDC applications. We have the isolated one, this of here. In this topology, we have a transformer in the middle, because here we are doing an AC-AC stage. We are transforming DC voltage to AC, then using the transformer to step that voltage, and then another AC-DC stage. This topology has some advantages because it allows to have switches with low requirements, even with isolation and for power. And a stepping ratio of this topology can be also higher, because we can go from a voltage of 1 to 10 times the other, in one side and in the other. And however, this topology has also some disadvantages, because designing a high frequency transformer, it's not easy, it's not an easy task. We have to take into account different things. Even when we have faults in one of the two DC systems, this can make issues into the transformer as well. The other topology that we have presented here is the non-isolated. In this case, we have no transformer in the middle, so here we are doing as well, we have a AC stage in the middle, but we are not using the transformer to step up the voltage. In this case, the stepping ratios can be lower because we are not using the voltage. For example, I think more or less 1 to 3 to say something. And in this case, the switches has more requirements because there is no isolation between the two DC voltages. And however, there are some topologies that has an inherent fault protection. So if a fault happens in this side, in a DC fault in this side of the converter, the fault will not propagate to the other one. So this is an important advantage to take into account.